Hello, welcome to our third video on parametric equations and applications in calculus. In this video, we're going to take a look at how to find areas under parametric curves and volumes of solids of revolution generated when those areas or regions are rotated about an axis. So we're going to assume here that we have parametric equations for a curve, as usual, x equals x of t, y equals y of t, for t running from a to b. Now, we're often going to assume there's also a Cartesian expression for the curve we're working with, at least in the area in which we're interested. We don't have to know this Cartesian expression. We may or may not know it, but we're going to assume it exists. Either that there's some function out there, y equals f of x, that describes the curve, or some function x equals g of y that describes the portion of the curve we're interested in. Again, we don't have to actually know what this function is, but it'll be a good way of thinking about our work towards area and volume. Now, if we assume there is such a function, y equals f of x, say, and x equals x of t, then by composition, the y as a function of t will be found by substituting x of t for x in the f equation. So we're going to use the result that then y of t will be this possibly unknown function f composed with x of t, or if we're working with the y variable, x of t can be given by substituting y of t into the g function. This idea, when applied in the context of substitution and integral, is an effective way to deal with volumes and areas involving parametric curves. So we're going to take a look at two examples of this in the remainder of the video. Start with the area under an arch of a cycloid. A cycloid is generated by a rolling circle of radius a and has parametric equations given by x of phi equals a times phi minus sine phi, and y of phi equals a times 1 minus cosine phi. We'll find the area under one arch of the cycloid traced by letting phi run from 0 to 2 pi. Now, as you may recall from the textbook or a previous video, the cycloid is the curve traced by a point on a circle as that circle rolls along a line. So in this particular picture, the circle starts here and then starts rolling. And when the circle is rolled to this point, the point P will have moved up here. The angle phi, as it turns out, is the angle through which P is rolled. So if we draw the line from the center down to the tangent to the line, and the other line from the center out to P, this angle is the phi referred to in the equations. So you can see from the picture as the circle rolls along the curve, when it goes through one rotation, phi will have gone through an angle of 2 pi, and that'll get us down to this other point down here. So we're going to suppose then that we have a Cartesian equation for this curve. We want to find the area under this curve, so let's assume there's some y equals f of x, which we don't know, but it's clear that this arc is the graph of y as a function of x. It satisfies the vertical line test. Now, one full rotation of the circle generates one arch, and the point P then travels from 0 to 2 pi a. The reason that's the case is that in going from this low point on the arch to this low point, the circle makes one revolution. The circle has circumference 2 pi a, and so the circle will have to roll this distance, so the x-coordinate runs from 0 to 2 pi a in generating this arch of the cycloid. Well, area under a graph is one of the first applications we learned for integration. If the graph is y equals f of x, and we're looking at x values between a and 2 pi a, the area under the curve is just given by integrating f of x dx from 0 to 2 pi a. Now, we don't know f, but we do know the parametric equations for the curve. So we're now going to make the substitution x equals x of phi. Remember, x of phi was given by a times the quantity phi minus sine phi. We'll make that substitution for x in the integral. So in that case, we're going to have dx d phi given by x prime phi, or a 1 minus cosine phi. And so multiplying through by d phi, we see dx is replaced by x prime of phi d phi, or a times 1 minus cosine phi d phi. Remember, we've agreed that if we plug in the x of phi into the f function, which we are assuming is out there describing this, then y of phi is given by f of x of phi. And of course, y of phi was a times 1 minus cosine phi. So our substitution of the integral would look like this. It is now the integral from 0 to 2 pi of f x of phi times x prime phi d phi, as we see here. The x of phi composed with the little f, and that gives us y of phi, which is right here. And over here we have what happens to the dx, which is the x prime of phi d phi. We change the limits from 0 to 2 pi a, which were x limits, to phi limits. Recall, phi runs from 0 to 2 pi as we generate one arch of the cycloid. That is, we have one complete roll of the circle. So we only have to evaluate the integral to get the area. And so we now have this area given by the following integral. To evaluate this, we would expand it. The a squared comes out in front because a is a constant. And then we expand the 1 minus cosine phi squared to get the expression in here. So this is not a hard integral. Remember, to integrate cosine squared, we use half angle and write it as 1 plus cosine 2 phi all over 2 d phi. And then the 1 and the 1/2 here give us 3 halves. So the antiderivative of 3 halves is 3 halves phi. The antiderivative of the cosine is the sine, so we have minus 2 sine phi. And then the cosine of 2 phi over 2 integrates to 1/4 sine of 2 phi. We put in the limit 0 to 2 pi. So the sine terms all vanish in these calculations. All that survives is the leading term evaluated at 2 pi. And we come up with 3 pi a squared, the area under one arch of the cycloid generated by a rolling circle of radius a. In our next example, we compute a volume. So we're going to work with pretty standard but important equations here. X of theta is a cosine theta, y of theta is a sine theta. If we let theta go from 0 to pi, these equations generate the upper half of a circle of radius a. As you plot this circle, you'll find that it starts on the x-axis at a0. This happens when theta equals 0. And by the time theta hits pi, we're over here. And the point has traveled around the circle, or at least a half circle, in the counterclockwise direction. We're going to consider the region under this curve and rotate it about the x-axis and find the volume of the solid swept out by that rotation. Of course, the solid generated is just a sphere of radius a. We've actually done that calculation before in earlier work, and of course you may know the formula for the volume of the sphere, so we'll tell if we're right when we get done. But we do this because we want to illustrate how to do this with parametrics. Now our strategy for finding volume was something of the following sort. We're going to start by pretending we have a Cartesian equation for this upper half circle. And of course we could write one of those down. We don't really care what it is. But y equals f of x has graphed this upper half circle as x runs from a to b. Now imagine a point x on the x-axis here, and we're going to draw a thin rectangle at this position x. This thin rectangle has height f of x, because y equals f of x describes the curve. We'll give it thickness of dx, illustrated here. When this rectangle rotates around the x-axis, of course it generates a disk, very thin disk, of radius f of x and thickness dx. And the volume of that thin disk turns out to be pi r squared. The radius r is f of x times the thickness dx. And then we, as usual, sum these small volumes by integrating. And so our expression for volume of revolution should be familiar. We're going about the x-axis. If we have a function y equals f of x describing a curve, It's just given by the integral of pi f of x squared dx. In this case, our limits run from minus a to a. Now we're going to see how to change this into an integral involving the parametric equations. So as before, we're going to make the substitution replacing x by the parametric expression for x. So we're going to substitute x equals x of theta equals a cosine theta. And then dx d theta turns out to be minus a sine theta. And so the dx is going to be replaced by minus a sine theta d theta. We change the limits of the integral to the new variable theta limits. And we can see that when x equals a, that's the upper limit. Then the upper limit a, that's an x limit, and x is a cosine theta. And that leads to cosine theta equals 1 or theta equals 0. So our new upper limit is going to be 0. And for the lower limit at minus a, similar work, shows theta equals pi, and that'll be our new lower limit. So with the substitution, the integral looks like this. Once again, the volume was given by pi f of x squared dx integrated from minus a to a. We make our change of variables. Remember the upper limit, a became theta equals 0, minus a correspond to theta equals pi. And we have pi f of x of theta squared, and the dx becomes x prime of theta d theta. Remember f of x of theta, since y is f of x. This is just y of theta, all squared, and then again the x prime of theta d theta. And y of theta was a sine theta, as we saw from the introductory equations, and the x prime of theta we saw was minus a sine theta. So we pull the pi out in front of the integral. Likewise, the a squared times a, the a cubed comes out, and the minus sign here was used to swap the limits of the integral. So we end up integrating sine cubed theta d theta from 0 to pi. This is not a hard integral, being an odd power of a sine function. And the way we did this was the following. So our volume looks like this. Pi a cubed in front, we have to integrate sine cubed. The way we learned to do that for an odd power of sine or cosine was to take one of the sine functions off to the side and write the remaining sine squared as 1 minus cosine squared. So this expression is sine squared of theta. And we've done the anti-differentiation right here. The intermediate step, if you like, would be something like this. You might try letting u equal cosine theta, and then the du turns out to be minus sine theta d theta. And that allows us to write this as an integral of 1 minus u squared, essentially, du with a minus sign. And then the u changed back to the variable cosine, and the u squared becomes 1/3 u cubed. That's where the 1/3 cosine cubed comes from. So we've kept this in the variable theta, so the limit stays 0 to pi on this, and you can check that if you put in those limits, you come up with 4/3 pi a cubed, which you probably recognize as the correct formula for the volume of a sphere of radius a. So the main idea in this video is that we can often start with Cartesian expressions for volume, area, also surface area works like this, arc length, centers of mass. Most of these geometric applications we learned in a Cartesian setting can be adapted to a parametric setting. And the rule of thumb is to write the Cartesian version of the integral, as we did, in terms of some Cartesian curve, either x equals f of x or y equals g of y. And then we made the substitution, x equals x of t if we're dealing with this form, y equals y of t in the g if we're dealing with that right-hand form, and change to an integral involving the t variable. You also may find we deal with arc length and surface area too, that it can be helpful to keep in mind These ideas, remember we saw earlier, dy dx can be found by computing dy dt over dx dt. So if you ever have a dy dx showing up in an integral, you can use this to get to the Cartesian forms. And similarly, dx dy is dx dt divided by dy dt. So thanks for listening. Good luck practicing with this, and we'll see you in the next video. Bye.